In our first video for this chapter, I mentioned that when light hits an object, it will do one of three things. Let's say that's your object. Light comes in, it hits the surface. The first thing it could do is be absorbed, raising the temperature of the surface. The second thing is that the light could pass through the surface, bending a little bit. This is called refraction. And the third thing is it could just reflect. We've talked about reflection in the last few videos. Let's turn our attention now to refraction. This video will talk about the index of refraction and Snell's law. So in general, when light travels through a different medium, it will travel at a different speed. But no matter what the medium is, the light will always be slower than the speed of light in a vacuum. And so we're going to compare the speed of light through any medium to the speed of light in a vacuum. So the index of refraction for any medium would be the ratio of the speed of light in a vacuum to the speed of light in a given medium. So here is a simple table showing the indices of refraction of a number of materials. Let's do a quick example. Let's look at crown glass right here. And we say, how fast is light passing through crown glass? So index of refraction is 1.52. Let's do this. So index of refraction is 1.52. And speed of light, of course, is 3.0 times 10 to the 8th meters per second. And we know that the index of refraction would be the ratio of speed of light divided by velocity of light within the medium. So speed of light then would be the speed of light in a medium would be equal to the speed of light in a vacuum divided by your index of refraction. So that'd be 3 times 10 to the 8th meters per second divided by 1.52. So we pull out our handy calculator. 3 times 10 to the 8th divided by 1.52 would give me 1.97 times 10 to the 8th meters per second. So it's significantly slower. Another way to think of this, if n is equal to 1.52, then that means that the speed of light would be equal to roughly 3/2 the speed of light within a certain medium. Because 1.5 would be 3/2. Okay, so light changes direction. Not only does it change speed, but it also changes direction when it crosses from one boundary of a medium into the medium, when crossing a boundary from one medium to another medium. Now that change in direction is our refraction. And we talked about our incident ray, which is the angle, or it's the light ray coming into the surface. And then after the light is refracted, that's our refracted ray. You have your angle of incidence and you have your angle of refraction. Now this can happen in both directions. You can either have light coming in from air into water, and you can have light coming from water into air. Notice that the path is exactly the same. It's just backwards from each other, so it works quite well. The only thing that's different is when light's coming from the air into the water, you get a little bit of reflection going back into the air. Whereas if the light is coming from the water to the air, then you're going to get a little bit of reflection off of that boundary back this direction. But now I want you to notice here, air has an index of refraction of 1.0. It's like 1.0003, close enough to 1.0, close enough to a vacuum. Whereas water has an index of refraction of 1.33. So whenever you're going from one index of refraction to a higher index of refraction, then notice that your angle is smaller. So that's what it says here. The ray actually bends toward the normal line. Likewise here, we're going from water into air, which means all of a sudden our index of refraction is decreasing because we're going from water to air. So because it's doing that, then our refracted angle is going to increase. The ray bends away from your perpendicular line. So this refraction has a tendency to make objects that are half submerged in water look very, very odd. So you have, say, a person's foot over here, light comes up, hits the surface, causes the light to bend. Well, your mind is used to saying, or it's seeing the light come from this direction, so your brain interprets the light from coming here. So your brain thinks that your feet are actually right there where your knees really are. And so as a result, you get some really crazy images like what you see here. And you see things like this all the time in the water. Now, how do we actually calculate the angle of refraction? Well, that depends on the refraction equation. We actually saw a refraction equation back in chapter 11. What we saw was that the ratio of velocities would equal the inverse ratio of the sine thetas. But when you apply the index of refraction equation, that n is equal to c over v, then you can easily solve that and you end up with this equation, which is that the n1 times sine theta 1 is equal to n2 sine theta 2. In other words, the index of refraction in one medium times the sine of the incident angle is going to equal the index of refraction of the refracted medium times the same sine of the refracted angle. Okay, I have to do a quick correction here. I said the ratio of v1 over v2 is equal to sine theta 2 over sine theta 1. I just did a quick search in your textbook. I have those backwards there. So that's really what it should look like. And so that is the original equation of refraction. If you use the index of refraction equation right here, then you end up getting Snell's law.